Hello everybody in this evening. It's with our pleasure that I welcome you to in this our third day session of this ATAL FDP, and we want to welcome you and hope you will enjoy this lecture also. And today our speaker of this session is uh, Dr. Sachin Kumar from University of Delhi. Dr. Sachin Kumar is currently working as an assistant professor in Department of Mathematics, University of Delhi North Campus. His PhD from IIT Roorkee and his area of specialization are non-linear partial differential equations, non-linear evolution equations, differential equations, Lie symmetry analysis, group invariant solutions, mathematical modeling, and general relativity. Dr. Sachin has guided 8 PhD students, and out of these, 4 are awarded and 4 are in process. He has also guided 5 MPhil students, and Dr. Sachin has performed a number of administrative responsibilities. He is also working as a potential reviewer for SCI, Scopus, and international journals. Dr. Sachin has published a number of best research papers in highly indexed national, international, and peer-reviewed journals that are top-ranked SCI journals. So the H index of is 26 and I-10 index is 53. Dr. Sachin has got 5 research projects with major grants. He has got many awards and distributions in his career till now. Out of these, in one, he has ranked among top 2% world scientists in the year 2022 in the single year impact in the field of applied mathematics. This survey is done by the Stanford University, USA, scientists for the top 2% of the most distinguished and influential scientists globally. During last 5 years, Dr. Sachin organized a number of conferences by the department and also attended various workshops, FDP and differential courses. So we are blessed that such type of personality with us today. So now let's welcome Dr. Sachin Kumar, who will deliver talk on analytical solutions and dynamical behavior of challenging non-linear partial differential equations using a variety of efficient and reliable mathematical approaches. So please, sir, come on the dice.
First of all, thank you very much, Dr. Anju Sani and your team for inviting me such a wonderful FDP in your university graphic era. Thank you once again. So today I'm going to present now my screen is visible. Please
Yes, sir.
confirm me.
Yes, sir.
Okay.
Yes, sir.
Okay. So today I'm going to present to discuss the analytic solutions of the highly nonlinear partial differential equation with the various efficient and the reliable mathematical tools. As we know that today the finding the exact solutions or analytic solutions of highly nonlinear equation is a hot topic, and to show the dynamical behavior of the obtained solutions. So in this talk, I have discussed first in the two phase. First phase I am discussing about the Lie symmetric method, and in the second phase I am discussing about the different other methods. So in the first phase I am discussing about the outlines are the introductions, what is differential equations, basic definitions, applications, generalized BKP, Gaussian equations, Lie symmetric method, and by using the Lie symmetric method to finding the analytic solutions. Yeah, as we know that the nonlinear partial differential equations plays an important role in to show the analysis of the complex nonlinear phenomena in the nonlinear sciences and the physical engineering. And there are number of examples on the physical modeling in various fields of science and engineering, particular in the field of plasma physics, nonlinear dynamics, chemical physics, fluid dynamics, etc. So what is the importance of nonlinear PDEs? Because the finding the analytic solutions, because there are so many researchers in the current era to finding the analytic solution, it is not easy as compared to the numerical solution. So in this my talk, I am discussing about to find the analytic solution with the different techniques. So first we see the Lie symmetric technique was introduced by the Sophocles Lie, which is the best technique obtaining the analytic solutions. The Lie symmetric is based on the invariance of the PDEs. So the Lie group of transformation gives an infinitesimal generators to finding the analytic solution. The applications of Lie group differential symmetry were mainly established by Lie and Noether. The elementary examples of Lie groups are translations, rotationals, and the scaling. What is differential equation? Yes, as we know that a differential equation is an equation that relates one or more function and their derivatives. Suppose, as we know that the simple linear differential equation can be written in the form of is dy upon dx, dy upon dx, dy upon dx, px y is equals to qx. And this is a simple solutions you can find. And suppose if we have the second order differential equation in the form of d2y upon dx square plus px dy upon dx plus qxy is equals to rx. So these differential equation we have discussed in the graduation level or a BSc level, and we are talking about only the linear differential equations. We are not talking about the nonlinear differential equation up to the MSc level. So in this my talk we will discuss the how to deal or how to find the analytic solutions of the analytic solutions. So the types of differential equation, yes, as we are aware that there are the two type of differential equation. Yes, the one is ordinary differential equation and second one is partial differential equation. The ordinary differential equation depends only one variable, one independent variable and one dependent variable. On the other hand, the partial differential equation depends only two or more independent variables. So the partial differential equations, some examples are, and as we know that some famous equations are the wave equations, Laplace equations, or the Laplace equations, heat equations, or a wave equation. There are three types of equations, and which can be written as in a linear second order partial differential equation in the standard form a del 2u upon del x square plus b del 2y del xy plus c del 2u upon del cy and d del u upon del x plus e del u upon del y plus fu is equals to. In this equation, if we take the b square minus 4ac less than 0, so we will give the dynamical behavior is elliptical form, and b square minus 4ac is equals to 0 parabolic form means heat equation, and the hyperbolic. But in my talk, I'm talking about the challenging nonlinear evolution equations. So the applications of nonlinear evolution equation is a hot topic in nowadays to finding the analytic solution or an exact closed form solution of the highly nonlinear partial differential equation in the various fields of nonlinear sciences such as plasma, ocean engineering, and there are many researchers to use numerical and analytic technique to study the nonlinear evolution equations. So nonlinear evolution equation is a particular case of the nonlinear partial differential equation. Sometimes we call about is nonlinear evolution equation inside of the nonlinear partial differential equation. So finding the analytic solution of these types of nonlinear equation is an important task in a current era. Yes. So to finding the analytic solution and to show the dynamical behavior of the obtained solutions, suppose in the form of, suppose here this is a W shaped form, and
Excuse me,
here
sir.
yes.
Yes, sir. Your screen is not means completely visible. You change the font means size.
Okay,
Change the font
just wait.
size. Yeah.
Now it is visible.
No, no. Means visible. It's visible. Screen is visible now. But that is a means your font. If it's bigger, it will be good.
Okay, just a second. I'll change. Now it is okay.
Yes, sir.
Yes.
Yes. Yes, sir. It's okay now.
Okay, okay. Thank
Yes.
you.
Okay. Yes, sir.
Okay, okay. So, so to show the dynamical behavior of the nonlinear evolution equation, the W-shaped and the V-shaped. So in the ocean engineering or waves, so we will see that this type of form is a V shape and the other form is a W shape. We will see if we flow the flow of the ocean, so the sometimes we get the solitone form of or a solitary wave of form of the waves. Sometimes we get the singularity form of solution, these types of, and we will discuss in the later case. And also we will get the lumps form of the solution, the dynamical behavior of the solitary verb solution. So in my talk, the some popular method to solve the nonlinear evolution equation. Till now, I am discussing. I have discussed only the what is the importance of the nonlinear equations and to finding the analytic solution. So these are some standard analytic method: the least symmetric method, Hirota method, Jacobi elliptical method, generalized conditional symmetry, exponential function method, inverse scattering method, hyperbolic tangent method, extended tan hyperbolic method, generalized exponential rational function method. So most of the researchers in today's days to apply this type of these method to finding the analytic solution. And I am basically apply the Lee symmetry method and a Hirota method because these two methods are the extremely powerful techniques uh, by the from the others methods. So the some popular nonlinear evolution equations. So 2 plus 1 dimensional KP equations. So first I am talking about the nonlinear evolution equation of the some famous equations. So here the 2 plus 1. Why it is called 2 plus 1? Here we see that the U is a dependent variable and T, X and Y. So X and Y and T are the independent variables. So we can write this equation del U upon del T, U del U upon del X, del cube of U upon del X cube plus sigma square del square U upon del Y square. So here, so we can write, yeah, we can say this is a 2 plus 1 dimensional KP equation. Similarly, some famous equation 2 plus 1 dimensional KP Benjamin BBK equations, 2 plus 1 modified CBS equations, because once we apply the least symmetric method, so we will see that key 2 plus 1 dimensional. So first applying the least symmetric method, so we'll get the 1 plus 1 dimensional equations. Means we can say so these are the some standard nonlinear evolution equations. Generalize PHKP equation, 1 plus 1 KDV equation, 2 plus 1 BLMP equations, and 2 plus 1 breaking solitone equation. So these are 2 plus 1 because 2 plus 1, why it is called 2 plus 1? Because X, Y, and T. So X and Y is means this is a special coordinates. So X and Y is 2. Suppose if we have 3 plus 1, so here the special coordinates will be uh, X, Y, and Z, and T denotes a 1. Okay. Suppose if we have the 4 plus 1, the 4 plus 1 means X, Y, Z, and W, and 1 represent is T. Okay. So these are the some standard form of the nonlinear evolution equations. The applications, the differential equation are commonly used in the physics problem. The sum is few well-known equation in physics. The 1 plus 1 dimensional wave equation means UTT means wave equation. As you are aware that the wave equation is one of the most important equation in the fluid dynamics. It describes not only the movement of string and wires, but also movement of the fluid surfaces. For example, water waves. And the 2 plus 1 dimensional Berger equations. So the Berger equation is a nonlinear partial differential equation which is used in the various field of the physical phenomena such as boundary, behavior, shock wave, turbulence, and etc. So But these example I am just to show why it is called 1 plus 1, 2 plus 1 or 3 plus 1, because applying the least symmetric method is depend on the reduction method. So 3 plus 1 dimensional KP equation is uxxy plus 3 uxy plus x utx plus. So here this is a nonlinear term, and this equation is a nonlinear partial differential equation with three spatial dimension, means x, y, and z, and t is a temporal dimension. So in this my talk, we have applying the least symmetric method to finding the analytic solution on a generalized BKP-Boschian equation. So the 3 plus 1 dimensional generalized BKP equation, this is my governing equation, and I am using the least symmetric method on these equations. Okay, so here V is a function of x, y, z, y. V is a function of x, y, z, and t, which is a wave amplitude along the three spatials and one temporal coordinates. Means three spatial means 3 x, y, and z, and subscript denotes the derivative with respect to the respective variable. Now why applying the least symmetric method? Because some researcher already dealt this equation by the different method. Suppose here we take the Dent et al. Constructed the rational form solutions by using the bilinear method. Wasman LNT applied the simplified Hirota technique to obtain the one solitone and two solitone solutions. The Verma and Core applied the truncation Penelevy expansion method to obtain the analytic solution. So that's why in the literature we have seen that the least symmetric method is powerful solutions to obtain the solution in terms of the independent functional parameters. So the application of symmetric method is reduce the system of differential equations. So suppose if we have the 3 plus 1 dimensional equations, so so applying the least symmetric method, we get 2 plus 1 dimensional equation. Again applying the least symmetric method, so we will get 1 plus 1, and again applying the least symmetric method, we will get the ordinary differential equation. Means my aim to reduce the nonlinear partial differential equation up to the ordinary, convert into the ordinary differential equation. These are the some basic books: P.J. Oliver, Blueman and Comay, the Blueman and colleague. Now, the least symmetric method to solve the nonlinear partial differential equations, the least symmetric method reduce it by one independent variable. So we cannot always find the solution of the reduced ODE. It is not general key we will always find the analytic solution of every ordinary differential equation or a highly nonlinear ordinary different. It depends how to deal the nonlinear partial differential equations. So integrability of the reduction equation must be checked if we use another method or the further reduction in case of the similarity transformation method. The dynamical behavior of the obtained solution give a important information about the physical behavior of the solutions. So now apply the Lie group of transformation method. So the Lie point symmetries. So here first we find the infinitesimal generator, because in my original equation means governing equation 3 plus 1, here the 3 plus 1 means x, y, and z and t. Okay, so applying this the least symmetric method on this equation means, because assuming one parameter Lie group of transformation. So this is a methodology of the Lie group of transformation. So first we substitute, we can write x star is equals to x plus epsilon xi x plus order of epsilon square, y star is equals to y plus epsilon phi plus order of epsilon square, z star is equals to similar way, t star and v star. Here these xi x, phi, xi, tau and eta are the infinitesimal generators, because once we apply the Lie group of transformation, so our aim to find these infinitesimal generators means xi x, phi, psi, tau and eta. So therefore the infinitesimal generator can be written in the form of means v is equals to xi del q upon del x plus phi del upon del y plus psi del upon del z, tau del upon del t, and plus eta plus del upon. So To apply the Lie symmetric method, these are the basic books: Blueman and Comey, Symmetry and Differential Equations; P.J. Oliver, Application of Lie group of differential equations. So because in my equation v triple x y, so we follow the prolongation of 4 times. The fourth prolongation of p r of v to generalize BKP equation. So we can write. So here we see that eta x, eta y, eta xx, eta xy, eta yt are the extended infinitesimal generators. So using this condition, the above prolongation use with the respect of the invariant condition to the generalized equations, so we will get. So this is the invariant condition of the governing equation. Means generalized BKP equations have this invariant conditions, and the extended coefficients and the total derivatives, which can be given in the details of the Blueman-Comey. So directly this method, so putting the value of these infinitesimals into the equation of this equation, so we'll get the desired determining equation. By solving these determining equations, we will get the infinitesimal generation. This is our aim to finding the infinitesimals. So solving these equations, so we will get this is xi x, means first I am recall that these are the x star, x corresponding xi x, y corresponding phi, z corresponding to xi, tau t corresponding to tau, v corresponding to eta. So solving these equations, so we will get the desired infinitesimal generators. So xi x is equals to c1 upon 3x minus 3t upon 2 f5. So here we see that there are 5 independent functional parameter. It is very rare to finding the analytic solution in terms of functional parameters. Okay, so here xi, the condition is this one, v, the infinitesimal generator, xi del x plus phi del y, xi del tau. So we can write this equation in a Lagrangian form. So what is the Lagrangian form? I'll be discussed later. So first we see that there are the two parameter, two constant c1 and c2, and there are the 5 functional parameter f1, f2, f3, f4 and f5. Okay, so 5 parameters and 2 constants can be written in the 5 vectors, means v1. How can we write this v1? Here the c1 corresponding x, so x by 3 del upon del x, okay, x3 del upon del x, and here also c1 is here, so phi is corresponding to y, so y del upon del y, okay, and here pi by 3 z del upon del v plus t del upon del t, v upon 3 del upon del t. Similarly, we can write for the other vectors for corresponding to c2, corresponding to f1, corresponding to f2, f3, f4 and f5. So there are the 7 vectors. Now by using the Lie symmetric method, so first we obtain the commutator table, because it's play an important role if the solution is closed or not. So by using the Lie brackets, vi vj is equals to vi vj minus vj vi, the commutator table is closed under the vector field. So by these vector means v1 v2 and v2 v1. So by construct this commutation table of the Lie algebra, so we will see that v1 corresponding to v1 we will get 0, v1 to v2 is minus 5 by 3. So we see that the v1 v2 is minus 5 by 3 v2, so v2 v1 is 5 by 3 v2. So similarly we see that the v3 v1 is minus 1 by 3 v3 5z f1 dash plus f1, so f3 1, so f3 1. So here we see that v3 v1 is 1 by 3, means this commutation table is a skew symmetry. Okay, so once you will get the commutation table is a skew symmetry, so it is a valid for the closed form solutions. So here we see that the commutation table is skew symmetric. Now to finding the solutions, we will assume the sum combination of the vectors. Here we take the first combination is v1. Suppose v2 plus v3, v1 plus v3, and here I am taking the 10 combinations of vector to finding the analytic solution. Now the group invariant solution, why it is called group invariant solution? Because the solution satisfies the invariant conditions of the Lie group. So that why sometimes the analytic solutions also called a group invariant solution for this equation. So in this section we will find the a number of closed form invariant solution for the corresponding symmetry by solving the Lagrangian equation. This equation arises from this condition, as I have seen from this condition, this one, कि dx upon xi plus dy upon phi, dxi upon xi plus dt upon tau and dv upon eta. So directly we can apply this form Lagrangian equations. So this equation is arised by the invariant condition. Now first vector field or a sub algebra v1. So here I am taking the first combination, means here the first combination is here x by 3 del upon del x, y plus del upon del y, vz del upon del z, t del upon this one. Okay. So the Lagrangian equation 23 for v1 becomes, because dx having the coefficient is x by 3, del upon del y means having the coefficient is y, and dz is having the coefficient of 5z upon 3, dt having the coefficient of t, and dv having the coefficient of minus v3. Now this is a very simple to solving these fractions, means dx upon dy. Now when solving, taking the first two fractions dx and dz, so we'll get one constant. Okay, now second this solution dy or dz and dt dz, so we'll get the four combinations, and the solution of the similarity solution is v x y z t is equals to capital V, because in my governing equation is on small v, and now I am taking the constant capital V in form of, means now this value, substituting this value, this small v value in the governing equation 14. Okay, now when we substitute this equation 25 into 14, so we will get the 2 plus 1 reduction equation, as you see that, because this is my governing equation, this is 3 plus 1. Why it is called 3 plus 1? Because x, y, z and t is there. But now applying the least symmetric method, we reduce one independent variable. So here z is removed. The reduction of z variables. So capital V x triple x y. So this is a 2 plus 1 reduction equation. Now applying directly the Lie group of method. There is an inbuilt program in a Maple software, so you can find the infinitesimal generator directly by the inbuilt program, but not finding the analytically to directly. So once we apply the Lie group of transformation on this equation, so we will get another infinitesimal generator for these equations. So xi x is equals to minus 1 by tan a1 a3, xi y a2, xi t is equals to a1 ev. Okay, so here we see that there are the 5 arbitrary constants a1, a2, a3, a4 and a5. Now assuming to finding the solution, we have a choices to find the solution, taking a1 equals to a2 not equals to 0, a1 0 or a2 0. It's depend to finding the solution. So I am taking the condition is a1 equals to a2 and the other constants are 0. Okay, so here we taking the a1 equals to a2 and the other constants are 0, and using the characteristic equation or a Lagrangian equations. Now solving this equation means this solving x and t, so we'll get x plus nt square upon 20 and y and t, so s is equals to y minus t. So using equation 29 in So the value of capital V into this equation. Now substituting capital V into this equation, so we will get the 1 plus 1 nonlinear partial differential equation. Here we see that the capital R and S. So here also is one independent variable is removed. Now again applying the least symmetric method on these equations. So the infinitesimals are xi r is equals to minus 1 by 2 b1 r plus b2 b1. So here we see that there are the 5 constant parameter b1, b2 and b3. Now solving this equation by solving this infinitesimal generator, so we'll get the GRS is equals to S minus 1 by 2 HW. Okay, and putting this value capital G into this equation, so we'll get the ordinary differential equation. So first my aim to suppose if we have the 3 plus 1 dimensional equations, so first by applying the least symmetric method, so you will get 2 plus 1, again applying, so 1 plus 1, and my aim to get the ordinary differential equation. So you will see that this is the ordinary differential equation, means h is the derivative of 4th power, h is 3rd power. Okay, so this is the ordinary differential equation. So as we are aware of that, the ordinary differential equation is easily solved analytically as compared to the higher order dimensional equation. So this is the main aim of least symmetric method, to applying the to find the reduction form and to get the ordinary differential equation. So here this is the ordinary differential equation, but it is non-linear because here h into h double dash. So this term is non-linear and we have no idea to find the solution, because up to the MSc level we will get the some methods only for the linear methods, but we have no other method to find the solution. Yeah, other method to find the numerical methods, but in an analytical way we have no other idea. So there is a one trick to find the solution of this form. Suppose HW. So here we're taking one polynomial form to get the solution. Suppose means HW. So here we're taking a solution is the form of means parabolic. Suppose y is equals to a plus bx plus cx square plus dx cube. Yes, sometimes we take a plus bx plus c upon x plus dx square plus e upon x square. So this is a assumption. Now putting the value of this polynomial, so we will get the form of this solution, and you will get here we take the two solution is a particular solution, but in a analytically way. Now putting this value, there are the two solution HW delta 1 minus 1 by tan W and HW delta 2 upon W minus 3 by. So there are the two solution. Now what be the solution, because the solution H is the form of, so H is here putting, so G will get, now G will get, so capital V is get and V is get means this one small v is get. So by using the backward substitution, so we'll get the solution. So you will see that there is a one exact invariant solution of the governing equation and second one. So it is very rare to find the analytic solution in the terms of. Now for this the dynamical behavior of the obtained solution means, so now putting the taking the some parameters, you have a some idea to find because these are the some wave form of the solutions, wave equation. So obviously you will get the solitone form solution. So solitone means the solitary or a solitone form is a solitary is a self-enforcing wave packet which maintain its shape when it's move in a constant velocity. So you will always get a solitone form of solutions. Okay, so here the three dynamical wave profile of the elastic interaction between the curved shape, because here it is a curved shape. These are the some lumps oscillating for the solution 36 when taking the parameters. Parameter is A2 is equals to minus 1.7, A3 is 31 because there is some parameters. Okay, so here, okay, now once we get when taking the first combination V1, so we will get two solutions. Now the second combination V1 plus V3, So you will see that the Lagrangian form of this combination V1 plus V3 is of this one. And solving this equation, because this is a Lagrangian equation, so the small v is of the form of capital V. Capital V is a function of x, y, and t, z. Okay, and in the integral form, and in a independent functional parameter. So now putting this equation, by solving this equation, the similarity form of this one, now substituting into the main equation, the governing generalized BKP equation. So this is also a 2 plus 1, because the governing equation is a 3 plus 1 dimensional equation. Applying the Lie symmetric method, so we'll get the ordinary 2 plus 1 reduction equation. Again applying the Lie symmetric method, because there is an inbuilt program in a maple, so we'll get the infinite symbol generator. And also we see that there are the 5 parameters, constant parameters. A1, taking the condition A1 is equals to, is up to you. These constants is dealing with you or not, but because it is very rare to because you will get a complicated calculation to finding the analytic solution. So you take some assumptions to dealing this type of equations. So I am taking A1 is equals to A2 not equals to 0, and others are 0. So here now solving these equations, so capital V is in the form of f rs minus 3 by 100 t square minus plus 10x. So here r is x plus 90 square by 20, s is equals to y minus t. Now this equation, this solution in putting in this equation. Okay, so you will get the 1 plus 1 ordinary differential equation. 1 plus 1 nonlinear differential equations. Again applying the Lie symmetric method, so you will get the form of this one, and you will again get the ordinary nonlinear ordinary differential equation. Now taking the assumptions is a polynomial form, means polynomial form, because here HW, so polynomial form is a plus bw plus c upon w plus dw square plus e upon w square and others. So here we take other two particular solution, and using the backward substitution fusion, so we'll get two solutions. So here we see that the solution, the obtained solution in terms of a integral equation or a independent functional parameter. Suppose if we take the functional parameter is a parabolic form, tangent form, trigonometric form, so these solution always satisfied these equations. Okay, so it is very rare to finding the analytic solution in this way. Yes, any query? So the dynamical behavior of this equation is three distinct dynamical wave profile of the lumps form of the solution, and taking the parameters is a naught, because here a naught, a1, okay, and f1 z is a naught z, and you have a choices to taking the parameters of sine z, hyperbolic, trigonometric function. So obviously this dynamical behavior will be changed. So now other combination we take V2 plus V3 V5. So I am directly, because the same procedure we will follow for the other combinations. So I am just discussing about the main solutions. So here once we apply, so in this case the 3 plus 1 reduces this ordinary differential equation, and the ordinary equation is here having the three solutions, this one, 2. So here we will get the three forms of different analytic solution in terms of an independent functional parameter or an integral form. So the dynamical behavior of the obtained solution. So here the three distinct dynamical wave profile of the elastic interaction between the curve shape, multiple lumps, oscillating multiple soliton, when taking the arbitrary of choices of this form of. Okay. Now again some applying. So other three forms of solution is here, these three forms of solution when solving this ordinary differential equation. So we'll get the curve shaped parabolic form, the three distinct dynamical wave profile of the elastic interaction between the curve shaped lumps, because here is a lump and the parabolic pattern for the solution 82. Because in the recent research to finding the analytic solution as well as to show the dynamical behavior of the analytic solution is a hot topic today. So the number of researchers working on this uh, by using the different technique to obtain the analytic solutions and to show the dynamical behavior. So in the first phase, I am just showing the least symmetric method, how to deal and how to obtain the solutions. So similarly, we can also solve the following nonlinear equations. Recently, the 3+1 dimensional shallow water wave equation, 2+1 dimensional Pavlov equations, 3+1 dimensional KdV equations, and these equations already published in a highly indexed journals, more than 3 impact factors. So it is a good to tackle the higher dimensional nonlinear evolution by using the Lie group of transformation method or a Lie group approach. So I am just to show the others equations. Yeah. So here just you see if this method is here. In this method we taking 1+1 parameter equations. Sorry, here we taking 4+1. Okay. This screen is visible to all. Please confirm me.
Yes, sir, it's visible.
Okay, so let's see, because this paper is a pure soliton and fractals, and I am taking here as a 4+1 dimensional focus equation. So I am taking here is a 4+1 dimensional focus equations by using the Lie group of technique. Okay, so once we see, so by solving again applying the Lie symmetric approach, same the Lie group of transformation method. Okay, the one parameter, so invariant condition and finding the infinitesimal. So here we see that there is a infinitesimal generators. Yeah, so here look at that, there are the 8 arbitrary parameters and 1 arbitrary independent functional parameter. But in my presentation I have just seen there are the 5 independent functional parameter and 2 constant. So here is a 8 parameters and the 1 arbitrary functional parameters. So same processing, I am here to finding the solutions. So let us see the form of the different dynamics. Okay, so I am taking here the combination of some vectors because here is 8 parameters, 8 constant parameter and 1 functional. So means there are the 9 vectors. Okay, so I am just see the solution of the form of directly. The main results of this paper. Yeah. And I'm pointed out the solution of the one researcher applying the Lie symmetric method and obtained these 3 solutions. Means only these 3 solutions. Only these 3 solutions. Just to see the results obtained by the Sadat et al. This form of the solutions and the our closed form solution. So here we see that the equation number 38, 35. 98, 99, 100, 111, 112, 113, and the number of solution and in the form of independent functional parameter. Here is the independent functional parameter, because if you have the independent functional parameter, so you have a choices to choice the taking the hyperbolic function, rational function, exponential function, and this solution satisfied. So I am just pointed out the applying the Lie symmetric method, so you will obtain the number of solution in the form of. So in this because this equation having the 4+1, so the dynamics of this equation is very beautiful to show. This is the three dynamical structure of the single breather type of form. And some others is here is parabolic form. The three dynamical structure of the oscillating, because here is the sum is the oscillating multi-solitones and the parabolic wave curves. And some other dynamics of the obtained solutions. So here you see that. So here the main work of the obtained solutions are having the reached dynamics of the obtained solitone solutions. So this is the beautiful is a highly extremely powerful technique to applying the least symmetric method to obtain the analytic solution, and as well as to show the dynamical behavior of the obtained solutions. So this is my first phase of the presentation today. So if you have any queries, so you presentations, now I'm going to present the other two methods, the application of generalized Kudrosov method and the generalized Riccati equation mapping method. So the overview, the introductions, explanation, how to deal with the technique, application of the methods, conclusions, and the references. So as we are already talking about the nonlinear partial differential equation have the extensive significance in the area of the applied mathematics and the applied sciences. So finding the exact solution of the nonlinear partial differential equation is important task for the nonlinear partial differential equation. Describe the complex phenomena in the nonlinear sciences, physical engineering, optical fibers, plasma physics, natural sciences, etc. So there are a large number of researchers and the mathematicians have developed the various effective techniques for commuting the exact closed form solutions of the nonlinear partial differential equation, such as the Jacobi elliptical methods, Heinz-Jordan method, generalized Riccati equation mapping method, generalized Kudrosov method, least symmetric method, Hirota methods, and other form of methods. So here, consider the following expressions show the nonlinear partial differential equation. Suppose if we have the nonlinear partial differential equation, so we can write in the standard form. Suppose I am taking the standard form of the nonlinear partial differential equation is in the standard form, u is a dependent variable, the derivative of u, ux, ut, uxt, uxx, utt, and the others derivatives, where p denotes a polynomial function of uxt with independent variable x and t. Here I am taking the two independent variable x and t, but in the my previous presentation I am taking x, y, z, and w already discussed. But in this equation, suppose the standard form, the nonlinear partial differential equation having only two independent variables x and t. So by taking this wave of transformation, so I am taking this wave of transformation uxt plus u xi e raised to the power iota xi, and where xi is equals to alpha x plus nu t and eta is equals to eta x plus eta 2t theta. So this equation, this nonlinear partial differential equation convert into the ordinary differential equations. So suppose the convert differential equation in the standard form can be written as so q u dash u double dash, means because the ordinary differential equation and ordinary differential equation is depend only one independent variable. So the dash the prime or dash represent the derivative with respect to xi. So where alpha, eta 1, eta 2, theta and the constants, nu is the velocity, where q is the polynomial functions, and the power of u represent the derivative with respect to xi. So what is the generalized Kudrosov method? So the step by step, the generalized Kudrosov technique is follows as. So suppose if we have the some generalized suppose if we have the first we taking the nonlinear partial differential equation in the standard form, so substituting the wave transformation, because so suppose if we have the nonlinear partial differential equation, putting this wave transformation, so this nonlinear partial differential equation convert into the ordinary differential equation. Okay, so this is my aim. Suppose that the possible exact closed form solution of equation third can be represented in the following rational form. So I am taking Just suppose the some trial solution form according to the generalized Kudrosov method. So the generalized Kudrosov method is given by the Kudrosov. So his technique use I is equals to P naught plus summation I is equals to 1 to L P I xi psi xi and Q naught plus sigma j is equals to 1 to M Q j psi xi. So where the Pi is 1 to L and Qj is from I to M. So these Pi and Pj's are the constant which can be calculated, where the PL and PM means the upper bound is not equals to 0, means this the value of Pi means and the PL means the highest value of these coefficients will be a not equals to 0. And suppose this xi u xi is the solution of the following ordinary differential equation. Suppose we take the first this trial function solutions and here this xi, because the u xi is in an ordinary form and I am taking the trial function in the form of xi, means u जो है depend किस पे कर रहा है, xi पे depend कर रहा है, तो other we take the other form of solution, xi is as take. So xi dash xi is equals to minus xi plus xi square. So this is a linear equation, and this equation having the solution of the form xi psi xi is equals to 1 upon 1 plus zeta e raised to the power xi. ओके तो बेसिकली क्या है कि हमने क्या किया था, इसमें ये सॉल्यूशन पुट किया है और उसमें xi की फॉर्म भी एक मैंने अदर सपोज कर लिया. तो xi का सॉल्यूशन अगर इस फॉर्म में है तो मैं एक सॉल्यूशन की फॉर्म फाइंड कर सकता हूं. So first we calculate the values of L and M, because the upper coefficients having the value of L, Pi having the value of the highest values PL and QM. So we can calculate the values of L and M by the balancing the highest order derivative with the highest order nonlinear terms appears in the equation number 3rd, and substitute the 4 into 3rd along with the equation 5th. Means first means substitute this value into equation number 4. Okay, so once we put the equation number 4 into 3rd along with the 5th, so rearranging all terms gives a polynomial of xi. So by equating the coefficient of 0, so we will get the algebraic equation. Obviously we will get the determining equation. So by using the mathematical software package or a Maple or a MATLAB, so you can solve the algebraic equation. So you can find the values of Pi's, Qj's, and ultimately we obtain the exact closed form solution of the governing equations. Okay, so first I am just discuss the first is generalized Kudrosov method. Okay, so Kudrosov method, and after that I'll discuss the generalized Riccati equation method. So first I'll deal. So I am taking the 1 plus 1 dimensional fold Gaussian equation atom in the zigzag optical lattice model. So I am taking this the governing model which is depend on the zigzag optical lattice model, and this model is developed by the Travolta, Raja J, and this one. So this is the zigzag optical lattice model. So finding the our aim is to finding the analytic solution as well as to show the dynamical behavior of the obtained solution. So here we are taking the 1 plus 1 zigzag optical lattice equation. So where here u is a complex traveling wave functions, and here delta is a space between two consecutive parts, and the Boson interaction in the optical zigzag lattice model is represented by V, is capital V. The interaction is attractive. I am just discussing about the physical significance of this equation. So when taking the V less than 0, so the interaction is repulsive if positive. Okay, the primary nearest neighboring hopping with the T1 greater than 0, and the next nearest neighboring hopping with this one. So this is the zigzag optical lattice model, and our aim to find the analytic solution by the generalized Kudrosov method. Okay, so use the wave transformation of Sachin, means here this is the partial differential equation obviously. So I am taking the wave transformation of this form, this one. Okay, now putting this wave transformation into the zigzag optical model. Okay, so once we put the wave transformation in this equation, okay, So we will get the reduced equation 9 into the real and imaginary part, because here you have a u modulus square, and I am taking the wave transformation is here u xi and e raised to the power iota eta, means I am taking the u in a complex number. Okay, so that's why I am split the equation into the real and the imaginary parts. Okay, so this is the real part of the equation. So we reduce equation 9 into the real and the imaginary part of the coupled nonlinear ODE respectively. So the real part gives this equation, equation number 10, and the imaginary parts, equation number 11. So here we see that the equation number 11 gives the velocity of the optical solitone in a zigzag optical lattice. So the equation 11 gives the velocity. And now the equation number 10 is a non-linear ordinary differential equation. Okay, this is the non-linear ordinary differential equation. Here is a non-linear because u raised to the power 3, means dependent variable having the 3 times multiplier, that is called is a non-linear. So using the balancing method, what is the balancing method? Balancing method is, suppose if you have the highest order derivative is equals to highest order derivative with respect to the highest nonlinear term. So here highest nonlinear term is 3u, u raised to the power 3, and the highest order derivative 2 times derivative. Okay, so balancing is apply here, means u raised to the power 3. So here we write n plus 3, sorry 3n. Okay, 3n is equals to n plus 2. Okay, so solving this, so the value is n is equals to 1. Okay, by applying, so the homogeneous value is 1. So the homogeneous balancing rules is implemented between u3 and u double dash, so which gives m is equals to 1. Okay, now to express the number of exact analytic solitone solution, we generate the homogeneous balancing, because the upper L and M depend on this. So having this is the generalized Kudrosov method. So L is depend on M. So L is depend on M plus 1. Okay. So first we find the value of M. Okay. How can find the value of M? Because U3 means highest order derivative. Sorry, highest nonlinear term is U3. U3 is, how to write is U3 means 3n. 3 multiply M is equals to m plus 2. Solving this, so m is equals to 1. Okay, m is equals to 1. Now relation 13 provides, means putting m is equals to 1 is here, so L is equals to 2. So hence the solution of equation number 10 can be written as, because I am taking, this is the trial function form. How we can write? Because I am already discussed this form. Okay, equation number 4. This p naught plus iota I is equals to 1 to L. L यहाँ पर मैंने अभी find किया, this is 2. Okay, RAM is equals to find किया मैंने 1. Okay, so we can write the form of this one. Okay, so now substituting equation number 14 into equation number 10. Okay, means the form of u in putting in this equation number 14. And following the methodology of the generalized Kudrosov method, so we show the following cases to obtain the exact closed form wave solution of equation number 9. Okay, so now putting the value of this equation, so we will find the values of p naught, because these are the coefficients, p naught, p1, p2, q naught and q1. Okay, so we will find the value of p naught is this one, depends on iota, p1 is also depend on iota, and p2. Here q naught is q naught, means arbitrary, and q1 is also q1. Okay, so you have a value of coefficients. Now substituting this constant p naught, p1, p2, q naught and q1 in equation number 14. Now putting this value on this, because finding the solution, finding the coefficients of the value of p naught, p1, p2, q naught and q1. So substituting this value, so we will get the value of u xi. Okay, and u xi is already I have taken. Okay, so we will get the solution on this form. I hope you will get how to apply the generalized Kudrosov method. So by backward substitution, means u की value मुझे u में small u में रखना है, so we will get the analytic solution in this form. Okay, equation number 15. Here we take zeta is equals to 1 and minus 1. Okay, zeta is equals to 1 and minus 1. Okay, For zeta is equals to 1 and zeta is equals to -1, the solution 15 gives the two different form of the optical exact closed form solution of the governing equation. Okay, so now if we take zeta is equals to 1, zeta is equals to 1. So when putting the value of this solution, how to show the dynamical behavior? This figure shows the evolution of the 3D plot, contour plot, 2D shapes of the equation 15 for the free choices of parameter when we taking delta is equals to 0.021, eta 2 is equals to 3, zeta is equals to 5, capital B is equals to 5, and is equals to 0.9, alpha is equals to 1. So you have a choices two free choices of parameter you will take. So here we observe that this figure A is a solitary wave because this pattern is a solitary wave profile, and the figure B is the contour shape of the given 3D shape, and the modulus U for this range. The wave propagation has been plotted of the equation number 2D. So this is the dynamical behavior of the obtained solution. Similarly, to find the solution, because once you apply the other finding of the solution, means here the set 1 p naught, the value have p1 p2. Obviously when we solve this algebraic equation, so obviously you will get 3 or 5 6, maybe a 10 14 number of sets. So here we see that the another set of the solution is p naught is equals to 0, p2 is equals to this one, q naught is equals to minus q1 upon 2, q1 is equals to q1. But in the previous set, q naught is equals to q naught, and q1 is equals to q1, and p naught not equals to 0. But is here in this set, p naught is equals to 0. Now putting this value in the solution number 14, the capital U is equals to this one, and capital U is a small u is equals to capital U e raised to the power iota xi, the main wave transformation. So by the backward substitution, we will get the another optical tone solutions of the governing model 9. So this is the form of 18. Now here taking zeta is equals to plus 1 minus 1 plus minus 2. So this gives the different form of the optical exact closed form solution of the governing equations. Okay, here is the cosec hyperbolic, okay, sine hyperbolic, the form of the. So the main constant is here कि once we find the optical solitone solution, the solution form in the terms of the rational form, maybe a rational form, sine hyperbolic form, tan hyperbolic form, cosec hyperbolic form, cot hyperbolic form. Okay, and the other set of 3 is p naught is equals to not equals to 0, p1 p2 also not equals to 0. So another set of the solution and having the solution of this form. Okay, so once we putting for the solution number 21, okay, this now putting the values, we have a free choices of parameters. So putting the value of eta 1 suppose 1, eta 2 suppose 3 theta. So you have to see that what is the, you will get the proper or a wonderful dynamics of the obtained solution. It is not a directly substitute the value of zeta is equals to 1 2 or 3, so you will get the dynamics. No, it is a some give the times to get the good results. So this figure demonstrates the evolution of 3D, and here we observe that this figure shows a singular form because it is a break here, and you see there the contour form of the solution. So there is the solitone. Solitone means a singularity. So there is some singularity at t is equals to 0 or minus t is equals to 0. So in the 2D plot, you have to see that there is some singularity in the given solution. Okay, so the wave propagation I plotted for 2D when t is equals to minus 2 is red. When taking the value, red is showing for minus 2, t is equals to 0 at 0, t is equals to 1, and t is equals to 2. Okay, now we have to show the another method of the generalized Riccati method. So first I just discuss one method, generalized Kudrosov method, and now I'm going to discuss about the generalized Riccati equation method. So first we see the first main equation. Here there is a methodology. So what is the methodology is here the nonlinear partial differential equation is the form taking the wave transformation. So you will convert the nonlinear partial differential equation into the ordinary differential equation. In the generalized Kudrosov method, we taking this trial function. But in the case of generalized Riccati equation mapping method, so here the important step of the generalized Riccati equation method. So we'll look for the solitary wave solution for equation number 3 in the following form. कि जैसे हमने रिकार्डी जनरलाइज कुद्रोसोव मेथड में एक ट्रायल फंक्शन सपोज किया था, इसी तरीके से हम जनरलाइज रिकार्डी इक्वेशन मेथड में एक हम फॉर्म सपोज करेंगे. इट इज आल्सो गिवन बाय द रिकार्डी. Okay, so here we take the form of my slide is changing or not? Please confirm me.
Changing, sir, changing.
It is changing now.
Yes, yes.
Okay, because there is some disturbances and suppose the internet is connectivity is not good. Okay, so I am just talking the okay. Yeah. Yeah. So generalized Riccati equation mapping method is here. So I am just taking the form of uh, capital U's here summation gk xi k epsilon xi. So so where gk is depend on k is depend on 1 to omega are the constant to be calculated. Whereas the generalized Kudrosov method is depend is L or M to find, but here is to find omega. So the value of the positive integer omega is to be obtained by using the homogeneous balancing principle. And here also in equation number 7, the functions Xi shows the solution of the following generalized Riccati form. So here I am taking the Riccati form, means psi dash xi is equals to del naught plus del 1 psi xi plus del 2 psi xi square, where this one is not equals to 0. Okay, where del naught, del 1, 2 are the constant parameters. So now putting this form 7 into 8. So first you will put the value of this one in equation number 7 and after that in equation number 3. So collecting the coefficients of xi x, so we obtain the set of algebraic equations. Solving this equation we will provide us the values of the unknown parameters. Okay, so substituting all this value in equation number 7, so we get the solution of the obtained solution. So I am also taking this model equation number 9. So now applying the generalized Riccati mapping method. Okay, so here, so in this section, the implementation of the generalized Riccati equation method. So in this section, we will see apply the generalized Riccati technique to obtain the novel analytic solutions. Okay, so by applying the balancing principle, the highest order derivative is equals to the highest nonlinear terms. Okay, so you will get omega is equals to 1, whereas in the previous method m is equals to 1. So here omega is equals to 1, the same method, homogeneous principal method. Okay, there is an important result कि these method only apply once you will get the homogeneous principles, means integer की value आपको मिलेगी तभी ये methods applicable है. On the other hand, linear similarity method आप apply कर सकते हैं. So there is some drawbacks of these methods. There are some method, Jacobi elliptical method, generalized Riccati method, generalized Kudrosov method. So these method only eligible, only valid for once you will get the balancing principle, means n is equals to 1, n is equals to 2. Otherwise, this method is not feasible. Okay, so omega is equals to 1. So we will see this method is applied. So the solitary wave form of this equation of equation number 10 is the u xi is equals to g naught plus g1 xi, where g xi satisfy equation number 8. Okay, so now putting this value into equation number the main wave transformation, so you will get the values of g naught, because we have to find the values of g naught and g1. So first set g naught is equals to the value of this one, g1 is this one. But the case 1, when rho is equals to del 1 square minus 4d, there is some assumptions for the case 1. The case 1 is the row is discriminant greater than 0 and the del 1 del not equals to 0. Okay, so the putting this value means g naught and g1 is here, so you will get the form of the solution, this one. Okay, so this solution is depend on the tan hyperbolic form of, and the second one is the cot hyperbolic form of. Okay, so the solution form of this solution, so this figure having the 3D contour and 2D for equation number 27 for the free choices of the parameters, the values of r. So here we observe that this represent a multiple solitone structure. You have to show that there are the some solitone structure, means there is a singularities. Okay, if you have to see that the through 2D figure, so you have noticed that there is a wave propagation with the different some solitone form of solutions. Okay, now so here the other forms of, so in the case first means there is the main importance of this method. You will get the for the set 1 for this condition delta 1 is 1 square minus 4 delta naught delta 2, so you will get the number of solution, means u3 is depend on the sin hyperbolic, u4 the cot hyperbolic, and these calculation I have done with my research scholar by the mathematical. So you can simply program this the method of this program. So you can implement, because there are the some important methods to finding the analytic solution, and there are the number researcher suppose from the Saudi Arabia, from Germany, they are applied this type of technique to obtain the analytic solution and publishing the paper in the highly indexed journals. Okay. So you have to see that there are the number of solution u6, u7, u8. These are the solutions, the number of solution. This depend on the cos hyperbolic and the sin hyperbolic. Other one is the tan hyperbolic form of the solutions. So here we see that the different form of the solution. For the solution is 30. This one. I have plotted the dynamical behavior of for this solution. Okay, so you have to see that there are the number of singularity, and these are the traveling wave form of these solutions. Okay, so the wave propagation has been plotted in the figure number C with the 2D for when taking t is equals to 0.2, so it is denoted by red lines. When t is equals to 0.7, it is denoted by green. T is equals to 0.85, it is denoted by blue, and t is equals to 1.3, this is magenta, for the range of -6 to 6. Okay, so it is noticed that the value of delta increase, the solitone amplitude increase, and the amplitude decrease towards the origin for the number values of capital U. And the other forms, so you can just apply and to finding to solving the algebraic equation, so you will get the coefficients of g naught g1 depending on delta naught delta 1 and delta 2, so you will get the number of varieties of exact closed form solution of this form. Okay, so for the case 2, this is I am when taking the case 1 when rho is equals to delta 1 minus 4 delta naught delta 2 greater than 0. Okay, so here we will get the 12 solutions, and when taking the solution of this form, so you will get u13 another form solution, u14, 15, 10 and sec form, 4 10 cos hyperbolic form, cosec form, tan and cotec form. Okay, so I am just taking a solution of 42 to show the dynamics of the obtained solution. So you have to see that the dynamics of this behavior. Okay, and the another solutions u19, u20, u21, 22. So you have to see that there are, you will get the number of solutions in the analytically form by applying just a simple method. Okay, and this is a is simply a beautiful figure for the solution 48 for this solution. When taking the free choice of parameter delta is equals to 2.2, delta naught is equals to 1.2, delta 1 is equals to this one. So here we know that this is a mixed periodic wave solitone profile. Okay. Another form of solutions, dynamics of equation number 49, this one. For case 4, when delta 2 not equals to 0, delta 1, delta 2 not equals to 0. So you will get another form solution U27. And the another set for 2, we will get another form of solutions. So you have seen that there are 38 solutions for this simple governing equation with zigzag optical solitone solution. And another solution is also find for the gamma is equals to this condition, case 3 and case 4. So similarly, we can find the more optical exact closed form solutions for the model 9 by using the following cases. And this work is already published in the Mathematics and Computers with the Simulation is a Q1 highly indexed journal. And so here the concluding remarks. So in this presentations, two methods, the generalized Kurotos method and generalized Riccati method, have been used to for the closed Gaussian atoms in the zigzag optical models to obtain the various optical solutions. The solution are expressed in the exponential trigonometric hyperbolic, including tan hyperbolic, cot hyperbolic, sec hyperbolic, and their combination. And we depicted the 2D and the 3D plots for the sum obtained solution, which including the periodic wave solutions, kink wave, combination of kink and multi-solitones, singular solitones, and the other solitary waves of solutions. So the main conclusion of this study will encourage the widespread use of the considered equation. The dynamical behavior of the solution demonstrate the offer approaches are sufficiently successful, may be applied to the another form of the nonlinear models in mathematics, ocean engineering, and the nonlinear sciences. Okay, so these are some references, and I am also see the published paper. Okay. So you have to see that this is the published paper in mathematics and computers and simulations. You have to see that this is the same methodology we applied, and you see that the number of solution in the form of. So I am talking about only 34, 35 solution in the presentation, but you have to see that there are the number of solutions 35, 36. Forty-nine, 50, and means from the generalized Kudrasov method we will find the 54 analytic solutions, and from the generalized Kudrasov method, so you will find number of solutions. These are the dynamics of the obtained solutions. So I hope these two methods is beneficial for attending this FDP, and you can apply this method to finding the analytic solutions for your governing equation, your governing models. I hope this presentation will beneficial for you. I hope so. If you have any queries, so you can ask.